I want to talk about three different things. First, I want to talk about the ADIOS interface and how the application, these big applications that we throw these big numbers around, what are they doing to get those performance? These two things that I want to focus, and if I have time, I will also talk about visualization, what are the challenges, and how we work with Kitware and researchers to bring ADIOS together with other tools to give a new tool set for the Exascale era in the visualization. Okay, so there are some links in the presentation that you can go for the documentations and the ADIOS source code and some examples that I'm using here. And if you have any concerns about building it or using it, then you can use the ADIOS to GitHub to raise new issues. We are not very professional about that. All the guys and ladies I'm working with it, they make the pride in their work and they answer very quickly when they have a solutions, but none of us really reacts when don't know what to say, and so start looking at the problem first and then answer later. So anyway, that's the place to raise issues and give us feedback on if something goes wrong. Okay, so Scott told about we have the self-describing data set, and we organize the data around variables and attributes. The variables are multidimensional distributed arrays, which has a type, and a multiple process holds the data. Single value is just a single value, someone is writing it. And there are two different ones. Either there is a global value that the simulation outputs, like the step or iteration that the application is, and the local one is that a value per process. For example, the rank of each process is a value that you can write. And then attributes are static information, that strings and values that you can assign to variables. So self-describing, what we mean by self-describing is that it doesn't matter how the data is stored and what is the file format. A human can list the content, the list of variables and the attributes, the types, the names, and the dimensionality, and then also gives the minimum and maximum value for that array in the data set. So for a quick overview. And then there are functions to read arbitrary portions of these arrays back. Whatever you want to read, a slice of it, you can read that with a function without worrying where the data is actually located, even though if it's spread across 1,000 files on the disk, you can still just read it with the same functions. You don't need to worry about it. Okay, so the n-dimensional array concept is that you define a type and just define a global space, and then every process declares its own block that it contributes into that global space. Right, so that's the typical use case of writing global arrays. Everyone is neatly fits in a block, and you fill out the whole global array. This is the easiest use case, and easy to write, easy to read. Everything goes very smoothly, but it's not forced. So you can create a global array, a global space, and then write overlapping blocks in there. So the processes don't align each other, but everyone writes stuff there. And then you can read this global array with the overlapping values. You get one of them, and by writing them, it's like overwriting one, and you don't know who is overwriting what. You get one value. Or one process can contribute multiple blocks into the same global array. And you also don't need to fill out the entire global space. You can declare a giant global space and then just write sparsely some blocks into that. And then the empty space is not written in ADIOS. If you know NetCDF format, you don't need to write everything. You can have undefined values or default values. The difference is that in the netcdf format, those empty spaces will be allocated on the disk, and undefined values will be written to the disk. So you have a big data, the whole global space is written to the disk. In ADIOS, only the actual blocks are written to the disk, and then you can retrieve that. Okay, the other, basically the one concept that differentiates ADIOS from all the other libraries is the step, the concept of the step. So in ADIOS, we don't write variables and attributes one by one to an output. That's not, or don't read that. What we do is we write a step, we read a step. The step consists of a set of variables and attributes that are output once and retrieved in a stream once. You don't need to read the entire content of a step. You can read portions of variables, whatever you want from a step, but steps are the basic entities going from producer to consumer. And so the producer is always doing output steps. You saw the begin step, end step function calls. All the puts that are per variable, they don't do IO, or whatever they do is the begin step, end step that will make it so that the entire data set is in the output. So it's all or nothing. And then the consumer gets an access to an entire step and then can decide what it wants to read and leisurely read stuff from it. And the step is guaranteed not to disappear while the consumer is holding to it. So in a streaming scenario, an application, a producer can be blocked by an in situ analysis or visualization process if it's set up so that it's producing data faster than the consumer can consume and process all the data. But you can also set up the staging in that sense that the producer can drop steps. And so the in situ analysis will get only the data that it can process, and the producer is not blocked. You saw Scott showing the video of the Grayscale simulation that was set up that way. So whenever visit joined, it just got the step what was available. And if it was too slow, then the producer the simulation just continued and steps were disappearing. What else do I want to say? Yeah, so one constraint in the design of the ADIOS API and the engines is that the step has to fit in the memory of the producer. So this whole begin step, end step business with the put functions basically prescribes that you start the begin step and until end step, everything that you say put, all this data should be fitting into the memory. And so that's the limitation, how big you can create the step. The step is not the application iteration. In most application cases, that's the case. The application iterates, and at some point, let's say every 10 iterations, it outputs data, or every 1,000 iterations, it does a checkpoint. So then, yeah, one iteration becomes a step, and the data in that iteration is written. But it's not prescribed. You can create a step whenever you want and keep building it as long as you want, as long as it fits your application. And so, but this limitation has been around for a long time, forever, since the beginning of ADIOS until the last release. In the next release, there will be a new engine which allows to go beyond this, and because there are some applications that really are demanding that building giant steps that are so big that it doesn't fit in memory. Okay, so the coding basics. ADIOS is written in C++, and so naturally it has objects. It's an object-oriented code. So, and it's written in C++, and then the APIs, the C++11, the C and the Fortran 90 and Python APIs are on top of that C++ library. And Even in Fortran, there are special types for these objects created so that you don't simply just have an integer for all kinds of objects, but each one has its own specific type, just for cleaner programming. So the first object is the ADIOS object that you have to initialize, just like MPI init. You have to create an ADIOS object, and then all the functions will be available under the ADIOS object. You can create multiple of them if you want, but one is usually sufficient. Then we have a variable object for every multi-dimensional distributed array. We have an attribute object for every attributes. And then we have the IO group that holds together all the variables and attributes that forms a step that goes into an output or comes in from an input. So you see most functions will be about IO functions. And then the engine is the actual object that will do the IO for you. So in the IO, we do all the definitions. As Scott said, ADIOS is declarative. So every process is just defining what they have, and you define what you want to see in the output, or on the read side, you define what you want to read. Every process just says, I want this piece, I want that piece. And then the engine is the one that will do the work and deliver the data into the memory, or deliver from the memory into the output. And then there are operators that work on the data while it's being put into the output stream, like all the compression works as an operator object. Okay, so in source code, you just include the ADIOS header file, and then you create an ADIOS object. The two optional parameters are a config file, that's an XML or a YAML file describing the things, runtime parameters for how ADIOS is going to run in this application in this run. And an MPI communicator. If you are not writing a serial code, then you can pass you pass an MPI communicator for all the processes who is going to participate in any of the kind of IO under these ADIOS objects. So this is either the global communicator or just a subset who is going to do IO. Then you create an IO object and you give a name. That name is used in that external config file to refer to it so that a user for the runtime can specify things for it, but otherwise it doesn't matter what is it called. That's not the file name. This is just a name for the IO object. And after that, you define variables, the arrays, and as Scott already explained, this is a two-dimensional variable. It will be called T in the output. It doesn't say anything what the variable is in the source code. This will be as presented in the output, and then describe the global dimensions, and then for every process, their local piece, starting offset, and the local size that they put into the space. And just for clarity, in the ADIOS API, if you have a C, C++, Python code, that's always row major. If you have a code in Fortran, MATLAB, or R, it's always column major. This is the most contentious topic among the ADIOS developers. So far, this is how it's set. So if you couple a Fortran code with a C++ code, or a Python code, then ADIOS takes care of flipping the dimensions, and XYZ Fortran array dimensions looks like ZYX in the Python or C++ code, and you don't need to worry about it. It's just, this is how it is. Okay, so how you write? If you just want to write a checkpoint, for example, you create an engine, say, and you give a name. The checkpoint.bp becomes a file name if that engine is a file-based engine. It becomes something else, the name of the stream, if it's a streaming engine. But for checkpoint, usually you use a file-based engine. You open this for write mode, and then you call put for all the variables that was defined. Var t was the variable that we define here, right? Var t, And then let's say T is the vector of the data in the local process memory. And so T data pointer is the contiguous data in the memory that is becoming that process specific block in the 2D space. And so you do all these puts for all the variables that you want to write here. For attributes, you don't need to write anything. By being defined, everything is known, so you don't need to do anything. And then you call close. And then the file will be written during the close. And therefore, it's important to know, to remember to not to change T, not to modify the content of T until you call the close function, because put doesn't write out the data. It just remembers that pointer to the T and knows that this is part of the IO that ADIOS needs to output. Some engines move, yeah.
Sorry, just a quick question just to make sure I understand as well, because there's no step here. So implicitly, there's already a step and a step because you're basically opening and closing, right?
But yes, sorry. So yeah, this is this is the simplest example with a single step. This is a checkpoint file. In checkpoint, usually you don't write multiple steps into it.
Yes, but if you wanted to alter T here, if you put it in, closed it in a step, like begin step, end step,
yes.
Could you then alter T? Because it's been staged.
Let me show the 2 slides later. I will show you. Right. So this was just the checkpoint. And so if you want to read back the checkpoint is very similar. It's just instead of defining, you create an IO object again, and then you create the engine to read in a read mode. It opens up the file, and now you can inquire the variables in the file instead of defining the variables yourself. So now you are looking for the double T variable. If you don't know what's in the file, then you need to use other functions to get the list of available variables and their types. And then you call get to get the variable. So VT is the ADIOS object description, and T here is a vector. You either create a pointer, a type double pointer, you allocate the data, you allocate the memory to hold the data, and then you pass that, or you can create just a vector, and then ADIOS will allocate on the vector when it's reading, and then you call close. So that's how writing and reading checkpoint works. And then so you just have multiple puts and gets for the variables that you wanted to write. And of course, if you want to read in parallel for the get, every process has to declare the set selection of which piece of that array they want to read. This example reads the entire data into the one process. Okay, so if you want to do more, you assign attributes to variables to make it more self-describing for the humans who are going to look at the data. And so instead of T, you say this is temperature, and then you create an attribute saying the unit is Celsius, not Kelvin. And then this is how it looks like in the output listing. There is the tool BPLS, and it just shows you this. You have a variable and an attribute. And so if you want to write multiple steps, then after open, you start a begin step, end step loop. And then you close this whole thing at the very end. So you can open this file or this output stream at the very beginning, and then you can close at the very end of the simulation. And then whenever you want to write a step, you call begin step, all the puts here, and then end step. So now the same rule applies. You cannot modify T until the end of end step. Right? That's what you were asking, right? Pascal, you asked this, right?
Yeah, I was just making sure that because normally I've seen ADIOS code, they always put in explicitly begin and end steps just because it's quite explicit. I just want to make sure that I'm not misreading it. Yeah, that's fine.
No. So usually this is how the code looks like. It's just for checkpoint. In any streaming scenario where you want to do code coupling, in situ analysis, you need to use these steps.
Yeah, okay.
Right? But the very basic stuff, I just wanted to show that, and at least it brought up this issue. So this is a good point to talk about these when you can modify the data, right? So you can modify the content of T after n step, because you don't know, you are the developer, you don't know which engine the user is going to choose. And what that engine is actually, how that engine is going to do the I/O. And so it might need that T until the end of n step, right? And this works for most application codes who have the data that you want to write out, because why would you change until you are saying I'm done with the I/O part? But other applications actually use temporary variables to prepare data for I/O, because let's say they have a giant, messy table, like whatever structure that is not, you cannot write out and don't even want to write out. You want to pick, down select data, what you want to do. And so you create temporary variables and, okay, this is my output. And in that case, they might use the same allocated memory for writing T and then U and then V and then X. In that case, there is an option to say, put sync mode in a sync mode. And then that tells all the engines that once they put call returns, the user is going to modify the data. Right? So that was not in this example. And so if you need to change the T before you reach end step, you must add a third argument here saying sync mode. And that will force a copy by any engine who cannot process the data immediately. They have to copy it, so then the application can modify it. And as you hear it, that's the reason why the default is this dangerous one, that don't modify it instead of the sync, because the sync always forces a copy. And even though it didn't matter until now, the next engine will rely on that. Really, you can save an entire mem copy of giant variables if you don't do sync mode, if you just follow this programming style. So it's very important to use it this way. We try to take away all the responsibility from the user to make the code correct and avoid like decisions for how I'm going to do I/O the best way in the source code. It's just declarative, but this is the one piece that we couldn't remove. Okay, I hope I answered your question fully. Okay, and then so you pick an engine. The picking an engine is that in the config file, you could say for that I/O, that's called simulation output in that example, please use HDF5 engine instead of BP4. So if you have parallel HDF5 on the system, you can build ADIOS with parallel HDF5. And then there is an engine called HDF5 in ADIOS, which is just using parallel HDF5 function calls to create an HDF5 file, just for the fun of it, right? So it's not implementing HDF5, it's using the parallel HDF5 library to write the data out into HDF5 format in case you need it. I don't really know any use case where you would need to do that if you focus on performance, but you can have other reasons, collaborations or existing tools that you want to have, and you really want the HDF5 format instead of any other file format. Okay, so let's focus on performance. Because reaching a terabyte a second is not easy, even on Summit, which has a giant file system and can support that. What do these applications that Scott showed, XGC, GTC, LAMPS, SpecFM 3D, and Vorpx and others doing over this terabyte a second amazing speed? So there are basically two things. One is that ADIOS is not writing a single file. When you have 1,000 compute nodes and many processes on each node, you have thousands, tens of thousands of writers. Writing to a single file is not a good idea. because it's just not going to work well. And so we don't do that. We write into a bunch of files in a directory. Every BP output is a directory, and there will be multiple data files, and some processes are going to write into those files. So we choose the number of subfiles for the capability of the file system. On small systems, you use 100. On Summit, you can go up to 4,000 and it can still handle that, but then the performance is going down. So there is no point to go over 4,000, definitely not. And the second one is to append multiple steps into one data set. So yes, we have a directory and we have a bunch of files in there to contain just the one output, but then it can contain those files can contain the entire simulation. All the 100 or 1,000 steps that the simulation writes out, you can write it into that. So I'm going to show you why these two things are important. So the not good approach, as was Alex is asking about the magic of why ADIOS is so fast. And it's only fast because we avoid the pitfalls of I/O. If you pick that my I/O should write a single file, doesn't matter how many processes, then it's not going to work. It's simple, there is a bottleneck at the file access, and then the processes just will wait on each other, and it will be very slow. The other option, the good old solution of Fortran codes, and using the Pawsey I/O, that okay, every process just creates a file with the rank as an index and then just write it, and it works great. It can saturate the bandwidth even at a small number of processes, and then at some point it will break the metadata server and break the file system server. It's basically at some point it becomes a denial of service, and then the processes just wait for the server to recover and answer a minute later. So those are not good approaches. So what we have to do is pick a number of files that we are going to write, and that number should be proportional to the capability of the file system, not the number of processes. You have n processes, the number of files is independent from that. Of course, it doesn't need to be more, but it needs to be picked for the given system. I said 4,000 is the top max for Summit. 2,000 is better. But 2,000, 3,000, 4,000 is usually the same. The more files you have, the more variability you see, so you have more chance for a bad day. The less numbers you choose, the less you can't reach the maximum bandwidth. So you can pick these in your application, set it, let's say I want 2048. Or you can say aggregation rate, or I want every 42 processes writing one file. 42 is the number of cores on Summit, for example. Right, so one of my colleagues from Berkeley did a test with Vorpx, and the ADIOS default mode now is it just picks one writer per compute node. So even though in this test there are 42 processes per node, and for some reason she did 42 nodes, so 42 by 42 processes, and that means the ADIOS engines implement an aggregation that 42 processes will give the data to only one selected process, and that process is going to write one file. On another node, another process is doing that same. So, and we have 336 files, then we have 36 processes picked on each node and writing one file each, 336 files in the file system. And that reaches, at that size, reaches over 650 gigabytes a second. It's not nowhere near a terabyte a second, right? But you saw this other application use 1,000 nodes, 512 nodes, 2,000 nodes. So this one scales very well. That's why you pick as a default value. But at smaller scale, you can pick a different number. So if you have 2 processes writing, every 21 processes doing one, their data goes into one file, you have twice as many files, and it scales better. I mean, it gives you better performance scales as well at this point, right? It scales very well up to 2000 nodes. And if you pick that, okay, every process should write the file, 42 gives you the best performance on 42 nodes, because you only write 1700 files, so it can absorb it from 42 nodes. It has fast network. It can give you the best performance on that small scale. But then if you just quadruple the size of the application, it will start to, choke the file system, and then the performance will go down very quickly. So, yes.
Norbert, can I ask a question? Just to make sure I understand this plot. Is it that you have there's MPI ranks, every core gets an MPI rank? It's not a hybrid code with like 2 MPI ranks and a bunch of open MP threads or a bunch of P threads. It's just MPI?
This example, yes, is just pure MPI, and 1 MPI task per 1 core. Yeah.
Right. Okay. Sure.
Right. So it depends on applications what you do. E3SM is, for example, running 84 MPI tasks on 42 cores. So you have 2 MPI tasks per core right now. But most of the applications use the GPU, because Summit is a GPU machine. So most applications use the GPU. And so they usually run 6 MPI tasks on the entire node, because there are 6 GPUs. And so 1 MPI task drives 1 GPU, and they use OpenMP to use the other CPU cores, right? 6 or 7 OpenMP threads, or 14 threads to utilize the CPU completely. And in that case, so we have much less number of processes, and the proper aggregation for SpecFM 3D Globe is just 1 writer per node. On 3,200 nodes, that's definitely the best pick. And that's how they reach 2 terabytes a second. There is the very strong aggregation, 1 file per node, and there is a large amount of data that's written to the disk. So it's the magic behind the number is that basically in the end, the step is collected, and there are many gigabytes on each node going to the file system. There is no small I/O involved, and different processes on different nodes are writing to different files, so there is no potential locking from the file system implementation, right? So nothing is blocking, everything goes very fast. Okay, so that what happens here, this is the basic recipe, the one thing to tune in ADIOS and running that. I have to pick a K number of subfiles, and that's the user's responsibility to pick a fairly good one, definitely not the one that will destroy the performance. And once the users figure this out, they want to write more data, because finally, with this speed, this scalability, ADIOS gives the ability for users to get away from that nightmare thing that everyone does, the lossy reduction of decimation. Everyone just writes every 100 step or every 10 step or whatever they can afford to keep it, to squeeze out as much information as they can and hope that they don't lose important information between. Now with this performance, they say, okay, I can write every single step. And now instead you have, just have 1,000 steps written out instead of 10 or 100, because you can. And in this case, another thing will become the bottleneck. After this is the big bottleneck. Once it's solved, there is a second one, and that is creating a new file every single step. That is everyone doing simply because there were no I/O libraries and solutions to give a fast way of appending steps to an existing file. Mostly because it's very dangerous. That what happens if my application dies in the middle of the I/O of that step 100, it corrupts the entire data set and the entire simulation is gone. So no. If that is stable, it's still, if you start to append things slow down gradually and then worse and worse and worse. So for performance reasons, no. And so with ADIOS, BP4, a new engine that Zhongling referred to in his talk, that's the new engine that allows to open a data set and just write the steps into it. And the append time is constant. And the file format guarantees that if that step is not written as a whole, the whole thing dies in the middle. The metadata is not scrambled, and you still see the n-1 step because the step n was not finished. So now you have a fast way of appending steps, and you are not going to ruin it, risking it by running it too long. And here is an XGC, another Fusion Code test, where we pick this F0 data set that is important to the scientists. It's a stress test in the sense that they don't really need every single step, but let's turn on and see what happens. And it becomes immediately obvious that as you go to 1,000 nodes, creating a data set to do fast I/O, which involves 1,000 subfiles, right? So it's a BP directory with 1,000 subfiles. It takes around 7-8 seconds, while with variabilities, 1 second to 10 seconds, whatever. But on average, it spends 769 seconds to write this data, 100 steps into the data, of which, if we just created it once, it's 37 seconds. So the I/O time is the write time is about 30 seconds, and the rest is just creating files. Right? Your other option is to choose another system, other library where maybe creating a single file is faster, but then writing to the single file will be so slow that that will be out of the chart. So you don't have a choice, really. You need to do these two. So you first do the aggregation properly, you get a big bandwidth output, and then your appetite will grow. And you say you want to write all the steps. Now you have to focus on this issue. So you append all these things together. So I want to. I think Scott removed the slide from here. Oh, okay. So then I will just skip this story. So, okay. So what? Sorry, I got off track. So another application is the Vorpx example. Is the same story here, that is a GPU code, 1 MPI task per GPU, 6 per node, and it's using AMREX, the AMREX library to do advanced mesh refinement calculations, and the AMREX has its own plot file, which is using this aggregation technique on its own. So they learned from us, learned from this, that this is the best way forward. So they already get a good performance. It's much harder to beat than other older libraries that don't have this in. So they already do the aggregation, and the light green gave some good performance. And then ADIOS, when we tried the first time to just replace that with the ADIOS I/O, we got better performance at scale, but it's nothing convincing, saying, why did we do this? Yeah? Any comment? Anyway, so yeah, so it was not convincing. Turning on that, adding the steps into the file gives us this great performance improvement at large scale. So it's important to see in practice, it's not that, we put in ADIOS and it will fly. It takes work and experimentation of doing these things right. So doing aggregation and then appending the steps. The other chart shows the difference between writing 1 file per process, so 6 per node, or 1 file per node. And writing 6 files per node, the bars were always better up to 256 nodes. At around 512 nodes, just 1 file per node started to become better. This is the pink dots. And so at 1,000 and 2,000 nodes, it's much better than writing too many files. Here you write 12,000 files in into the file system. Even Summit GPFS doesn't like that. Okay.
There is a quick question from Alexis. How many time steps per aggregated file?
I don't know. I don't know. It's not a million, but I mean, technically you could a million. The thing, what you will pay for is that the data set becomes one big giant, very, very big data set. Right? So if you write petabytes of data, if it's just one directory with 1,000 files, each one is many multi-terabytes files, and the directory is many petabytes. It's hard to handle. The other one, if you want, when you open it for reading and you want to see it, there is a metadata cost that increases linearly with the number of steps stored. And that's why a million is not something, a multiplier that is just too much. So I don't know. 1,000 seems to be okay, but it could be too big. Was that the question?
Yeah, exactly. Yeah, thanks, Norbert.
Right. Okay. So another just typical approach to I/O has been the old codes, aggregating everything to a single process and then writing it out. Atomic simulations do this for some reason, is because they deal with just a handful of atoms, not trillions of atoms, just thousands and hundreds of thousands and maybe millions of atoms. So you can just collect it on a single process, write it out, and call it a day, right? And it's supposed to be very fast, but it's not. So we tried with NWChem. The challenge was, can we write every single simulation step to the disk? Because the scientist has to decimate, and in practice they just write every 100th step. But then, you know, they miss the chemistry where things happen is so fast that they just miss that. So they would like to write every single one and then, you know, throw away later, but just keep the sections that are important. And so changing to ADIOS, and every process is writing it and doing the aggregation in ADIOS itself, is so fast in NWChem and in LAMPS that you can just write every single step to the disk and don't worry about it anymore, right? It's a kind of a counterintuitive, because you're supposed to do it right, but it wasn't. While you are aggregating data in the application to one process, it's part of the I/O and you are not writing anything. So that adds the time together, and then your I/O is really slow. Okay, just for the reading a little bit, for that I have to explain the storage pattern of the data. So logically contiguous is what the netCDF data model and the original HDF data model did. Each variable is stored on disk as a one contiguous buffer, right? Like in a in the era of serial processing, you have a variable in memory. It's just a contiguous allocation in a one-dimensional array in a memory. That you write it out is just a one series of bits on the disk. And that model forces you to data reorganizations, heavy reorganizations, both at writing and reading. When you write out the data, you have each process has a block of data contiguous in its own memory. And as it's written to the disk, it has to be reorganized element by element, or in 2D case, it's line by line of the 2D arrays into a logically contiguous big format. So there is a high cost and synchronization between processes to create these simple single one giant line of data. And the same happens when you read. If you want to read a block, you have to read line by line from this 1D array to create this block, right? So you have to have a lot of seek and just reading tiny piece of one lines of a 2D blocks, or if you have 3D, it's even worse. So you have lots of small I/O in the background to implementing your big block read. So this suffers twice big data reorganization. ADIOS chose a different path, saying we don't do reorganization on write, we do reorganization everything on the read. So you don't pay any cost of reorganization. Every process block goes into the output somewhere as it is. Both staging and file writing, it's just going that way. And so now at read time, when you want to read a block of the global array, that has to be assembled from multiple small blocks. So ADIOS has to bring in these 4 blocks here to construct the P2. The good news is it doesn't need to touch most of the blocks, only the ones that contribute to that array. And then that's how, hopefully, would be better, right? And we showed this more than a decade ago that indeed, in most read patterns, this is actually better. And then HDF5 introduced a new format for parallel I/O, the chunking, where you define a fixed size of chunks for I/O purposes. And now on the right side, you do reorganization for moving data blocks into chunks. And then when you read from chunks. So these are the different approaches. And, you know, on the read side, well, so let's see. On the read side, this is the bottom chart. This is the 6 basic read patterns of the Vorpx application, reading the entire array, reading 2D slices in each direction, reading a sub 3D block and a sub 2D slice in a plane. This is what usually the users of Vorpx are doing in the read side. And the thing is, logically contiguous file format is superior in most of the cases. So the users would say, I just want to use this basic logically contiguous format because it's better if I use my scripts to read the data. The bad news is that the logically contiguous is just not able to write out the data. We are talking about many terabytes per step and lots of processes, and the performance is just abysmal. It's impossible to write. So you only have a choice of doing chunking or using chunking plus subfiling, which is the ADIOS way of doing the no reorganization with the blocks and using subfiles and aggregation. So in this case, orange is what HDF5 with the chunking you can do. But if it cannot go further because it's still writing a single file, but it's way much better than logically contiguous, right? So this is your option 1. The option B is use ADIOS, and then the subfiling and aggregation gives you a better scalability. So on hundreds of nodes here, Vorpx has more than an order, 2 orders of magnitude better performance. So it can output these tens of terabytes per step in a time so that it's just a small part of the application time. With chunking is still overwhelmingly an IO bottlenecked application. But so these are the 2 options. But then unfortunately, like if you read the wrong plane, it takes a long time to read in. So what we learned is that, interestingly, having multiple subfiles, the data spread in multiple files. If you start reading in parallel, doesn't matter but the entire variable, if you look at squint and look at the trend of the green bars, in every case, it starts to improve. So if you read in parallel, then you can get good read performance from a giant ADIOS files which has subfiles and lots of blocks. And basically that's the moral of the story. When we have tens of terabytes per step and hundreds of terabytes in a giant data case, reading from a single process is not a viable option anymore. I mean, you wish you could, but you can't, because the only way, if you want to read the slices that has good performance with logically contiguous, but you cannot write them, so it's out of the picture. Every other viable options will force you to go parallel. I mean, there's node that 32 is just a 32 cores on a single node in a cluster here. So this is just running Python on a single node and running multiple processes to read in the data. And then it can give you nice performance, but you just cannot do single processing anymore efficiently. So that was what I wanted to say. And we have only 1 minute left for Python. The point is that you have to use MPI now. So we can use MPI for Py together with NumPy and ADIOS to read in data. So once you open a file, you can pass the communicator just like in the C++ code to do parallel operations. And when you want to read a data, you can use the offset and local size for each process that you want to write. So basically, that's the Python API of saying, I just want, well, this one reads the entire thing and all the steps in a file and reading a slice starting from offset 0 to 10 to 16. But so in parallel, you can just do it just like in a C++ code. So it gives you very easy access in Python to write a parallel code. The only work that you have to do, and in the links to the Grayscott example or the heat transfer example, you can look at the Python scripts. What it deals with is to calculate the 1D or 3D decomposition of an array to determine who reads what. And that's the same problem on C++, Fortran, or Python is true. You have to write that code. But otherwise, reading is possible and using MPI. So we run out of time. I will stop here. If you have more time, you can ask questions and I will try to answer them. Thank you very much for this attention. I know it was 2 hours straight. It was dense.
It is a bit intense, that's right. Any final questions? Please unmute yourselves and feel free for, either for Norbert or for Scott.
Oh yeah, hi everyone. Yeah, Norbert and Scott, I just had a question about fault tolerance. So I'm aware that you have a directory and you have a whole bunch of files in that directory. So if one of those files were corrupted, for example, what sort of fault tolerance do we have? Is there a manageable degradation of quality, or do we have to throw out the data set?
Yeah, so multiple answers to that question, I guess. So if you mean the data set becomes corrupted at step N, because as I said, you append all the data and your application dies in the middle of I/O, and not all the data goes out. The metadata is created last, and so it's not going to be present, even though the data fractions are in the file. because of the all or nothing nature of writing out the metadata at the single process at the very end when everything is done, it's not visible. So you only see n-1 steps. Now we say if you go in and trash stuff in one file, what is there is the data of several processes. And so your global array, which consists of many local arrays from many processes, some of them is corrupt. And I think the major problem is, how would you figure out that it's corrupt? So right now we don't have any tools to tell you that some data blocks is corrupt. So you read in everything and all the reads will succeed because you just get some pieces of the memory encode the corrupt data, right? And so there is no mechanism to say you can gradually keep something of the data to some error, right? And then if you like it, you can have it, otherwise you have to throw it away. Basically, those processes data is completely corrupt. There is no did application have multiple copies or get something. So that's the basic answer. But Scott would be waving that that's the whole. He wanted to show you that he calls little Einstein diagram with the climate data to have multi-level decomposition of the data using the mGuard lossy compression to have multi-resolution data in different levels of the storage hierarchy or different files. And in that case, you could read in progressively data always, not just if you have corruption somewhere, but saying, I only want visualization to 10 to the minus 3 accuracy, then you only need to read a fraction of the data from some files to do that, and you don't even need to read the entire data. So that gives you this gradual stuff. So if you have the large component of the data, which is the last full accuracy is corrupt, you can still read back the data to a given, the one before the last accuracy, let's say 10 to the minus 6. So, but there is always a conflict with answering anything, because ADIOS is a product where if your user asks a question to me, is this done? Can I use it? That's a different answer saying ADIOS is a research project. We have lots of collaborations, lots of interest, and we are trying to develop new solutions. And this is one of the big things that we are focusing on. My story was about, we give you very fast I/O, terabytes a second on these systems. People want to use it. They want to write suddenly 100 petabytes of data out because they can with speed, but then there is no storage, of course, and they cannot process it. So now the second one is, we need to reuse the data and give tools, integrated tools that gives you these solutions together so that you can rely on them and you can mathematically prove that this is correct. You can track cyclones and in compressed data, and you can make sure that that cyclone is actually exists in the real data that was not saved. And so in that case, fault tolerance comes from that. But that doesn't exist today, right? In some forms, prototypes and publications, we have that, but it's not a product today. Okay, sorry, that was an exhaustive answer. But for every question, is this really, this dual nature of ADIOS comes into play. And I'm the product guy, Scott is the research guy. Okay.
Thank you for that, Norbert. And Toby, did that answer?
Yeah, that's a very comprehensive answer. Thank you. Yeah, no, I was just thinking if some of the data was corrupt, I would like to know about it. But if I was desperate to get at that data, like it was really valuable, I would like the ability to do that as well. So yeah, that's what I was thinking.
these questions come up, but you see also there is a millions of ideas, and we always have to pick what we develop for the actual application asking for it. If we had an application collaboration that this is the important stuff, it would become with the CRC, as we have min-max for every piece of block written, every process. You know, we could check if the data is actually min-max in the min-max range, and if it's not, we could raise a flag, this is corrupt. But it's not 100%, right? It's just if you go out of min-max range. We could do CRC codes and then error, you know, MD5 sum codes or even error corrections to some level and do that. But it's never been, you know, the important part here. So yeah, as a research part and it needs work, someone could do it. Yes.
Okay,
so
and we have one question. I think maybe you can see from Lucas, he doesn't have a microphone.
Yeah, this is a very important question, right? What is the longevity of ADIOS? Well, he's asking specifically the ADIOS file format. Can I read back my data 5 years later? But it's basically the longevity question, right? Because what can I rely on a software? This is data, and I want to read it 5 years, 10 years, 30 years later. So that was, we start with Andreas talk about the CASA core has been the radio astronomy de facto software and the format for the last 30 years. Changing that is very risky. And they went into this saying, okay, ADIOS gives the performance that we need for SKA. This is our basically only option at the moment. There could be others coming in down the line, right? But changing the CASA core tables format for all radio astronomy to ADIOS file format carries this risk, not for 5 years, but for 30 years. And 30 years is a very long time. So as Scott showed in the production with this ECP program, we really focused on building ADIOS as a framework that has very rigorous testing, 2000 tests for every single commit that cannot progress until it works on all compilers or systems that we have tests for and all the test passes. And then that's just one thing. The second one is how is going to ADIOS as a software survive long enough so that you can read it back, right? And then it's basically one of the Department of Energy's proud child is ADIOS code that's been developed in Oak Ridge and with collaborators. But it's still part of the research and development community, right? It's not a company that earns money on that product, and if the product dies, the company dies, or the company dies, the product dies, right? It's hard to predict what DOE is going to do with this. They definitely like it because the biggest applications on the biggest computers are using ADIOS and relying on that. So I'm a small guy. I don't know what can I promise you personally from what the US government and the Congress will approve and how long ADIOS is going to be supported. But it's been going on for 15 years and it's flying and everyone likes it. And so it's a very stable software. Very stable software, and the funding and the people around is just growing. So in 5 years, definitely it will be around and you can read back your data. Because then on the development side, we have BP3, BP4, and the next one BP5. So now we will have 3 different ADIOS file formats, but we can always read this back because the engines that do the writing and do the reading is in the ADIOS. They don't change, right? You have a new version. It has one more engine to deal with the new versions, but there is the old engines to deal with the old versions. So yeah, definitely you can read back 5 years from now, just like as we can read XGC data from 12, 15 years ago that were produced.